Hello everyone, this is a data structure class, and today we will go on chapter 7. Title is sorting. Yes, this chapter sorting is not uh, about data structures. It's not a new kind of data structures, but this sorting is necessary for the applications of data structures. So after we design data structure, usually we will search some data from the data structures. Okay, at that time, we need the data, given data is sorted. Okay, because once we are given sorted data, the searching is very fast. But if we are given unsorted data, the search may take a very long time. Okay, so many applications try to search some data stored in some data structures. Okay, so chapter 7 will introduce about what kind of sorting method are available. So it's also very fundamental algorithms in many applications. Okay, if we consider sequential search means that it is a very brute force search method. Okay, so it's a very novice search method. It's not efficient or professional search method. So sequential search method means that if we are given data like this data structure, like element will have key values, and other field data are stored in this data structure, and we have some array to store this type of data. Okay, so in this case, the data size is maximum data size is 1000, and this data is a given input data. In here, I want to search some data with which has some key values. Okay, so key value is such keyword in this given data set. It will return the list I. I means that the index of this array, input array, and this I key values are equal to the such numbers, such keyword. Okay, in order to find the same such keyword in the array, we must search all of the data using this for loop. Okay, and then we will check the key value is the same as such number. Okay, so once we find the index or the same keyword, then we can find the corresponding index values. Okay, so if I is greater than n, that means that we cannot find the such number in the given data set array. A. So it will return 0. Otherwise, we will return the found I values, index values. This is a sequential search method. That means that we will search from index 0 to n values given data set. Okay, it's just a brute force method. So this is a sequential search example. So we are given 1, 2, 3, 4, 5, 6, 7, 8 values are given. Okay, if we cannot find such number, then we have to compare or evaluate n plus 1 times. So the average number of comparison for the successful search is that if we find such a number at one time, this is 44. If we search 44, we can search. We can succeed to search the 44 number at one time. Okay, that is 1. And if we find 55, then it will be found 2 times. 3, 4, 5, 6, 7, 8 times are necessary to succeed to find such numbers. That means that this we will summation all of the necessary comparison values using this summation, and this is average number, so we will divide by n. Okay, this number is becomes 2 n plus 1. Okay, and this n will be divided by n, so the result is 2 n plus 1 is average number of comparison necessary for the sequential search method. Okay. But if we have sorted list as an input, then the search becomes very, very efficient or very, very fast. That search method is called binary search method. Okay, so the sorted list means that all of the key values has increasing orders here. Okay, then if we wanted to search some values, such number, then we have to compare with middle key values. Okay, if the such number is less than middle key values, then we will search only left part of the given sorted list. Okay, so that means that we will search only A1 and A middle minus 1. Okay, that is a left part. And if the such number is the same as equals to the middle key values, then we succeed to find the such numbers. So we will terminate the search successfully. And the others, the else is such num is greater than middle key values. Then that means that the such num will exist on the right part of the input array. Okay, so that means that we will search only A middle plus 1 index and A n. So this is the right part of the input values. Okay, so using this, this is called the binary search. Okay, if we use this such method, then we can find such num values very quickly in compared with if we are given sequential search in compared with sequential search. Okay, so this sorting is very important in the search method. Okay, this is another example of a binary search method. Okay, so if we are given this input data and this input data is already sorted, increasing orders. Okay, increasing order. Okay, if we are given this input data, we can construct this kind of a binary search tree, decision tree for binary search tree. Okay, so now after we have this data set, we can find 56 data as follows. Like if we will start from the root node, so if 56 is a such num, this such num is greater than 46. That means that this such num will exist on the right of this trees, decision trees, binary trees. Okay, so we will go to the right side, and we will compare 58 with such num 56. Then such num is smaller than, less than 58. So we will go to the left side. And how about this one? 48 compare with 48 with 56 such num. Then such num is greater than this 48. So we will go to the right. Okay, now this 56 such num is found. Okay, how many comparisons are needed to find 56? 1, 2, 3, 4. Okay, so that is the same as with the height of the trees. Height. Okay, so we can understand that in order to find such num using this binary tree, the necessary number of calculation, number of comparison calculation is big O log n. Okay, log n is the same as height of this binary trees. 2의 n. Okay, so we can understand that the binary search is a very fast rather than sequential search. But in order to use binary search, we have to given input data as ordered or sorted. Okay, so the sorting method is very important. Okay, this is a binary search algorithm implementations. Okay, so this binary search input is A, And of course, this A array is sorted. And also, such num is input parameter, and n is the number of data set. And left value, initial value is 1, and the right value is n, and the middle is not initialized. Okay, left is less or equal to right, and middle value is the middle of between left and right divided by 2. And compare middle key values and such num. If this case -1 means that the key value is less than such num, then we will adjust the value of left value as middle plus 1, means that we will search only right part of the given data set, and its case 0 means that it is equal. The key value and the search num are equals. Then it will case 0, and it will return the middle values as the found index in the given data set. And the case 1 means that the key value is greater than such num. Then we will adjust the right value of the such data set, okay, as middle -1. That means that we will search only left part of the given data set, given sorted data set. Okay, so this is the same implementation of binary search as we explained in the previous slide. Okay, now we can define what is a sorting problems. Okay, so we understood that sorting is very important in the search method. Okay, so we have to define what is sorting problems. So if we are given this data set as a record R0 to Rn-1, each record has a key value ki. Okay, then sorted means that the key values are smaller than key values of I. So key values of index I-1 is less than key value of index I. Okay, so that means that this is increasing order sortings. Okay, this is sorted. Every record are sorted that satisfy these increasing orders. And what is stable? Stable means that if I is less than j, and there are the same key values exist in the record input data, then Ri, I is less than j, Ri precede Rj in the sorted list. Okay, that is stable. That means that the order of the equal data is maintained in the sorted output. That is stable definitions. Okay, so this stable definition will be explained more in the next slide. And this criteria to evaluate which sorting problem is better, sorting method is better or not, is here. Number of key comparison is important criteria to determine which sorting method is better method, better algorithms. Or number of data movement is also another criteria, but this comparison, number of key comparison is a more important criteria to decide which sorting method is efficient method. Okay, and we will look at stable definition more in the next slide. So stable sort means that the two objects with equal keys, two records with equal keys. Yes, the same data exist in the input data, then the same order in the sorted output as they appear in the input array to be sorted. Yes, that means that the orders are maintained after sorted. That is stable sorting method. So for example, here input data is 1735479. So there are two equal 7 here. So the first 7 is represented as a 7 1, and the second 7 is represented as a 7 2. So the this is here input data, and if we sort to the list, then the output is here 1 3 4. Yes, it is sorted increasingly, and 7 1 is here, 7 2 is here. So the A output is called stable because 7 1 comes first in the output, sorting output. That is the same order as input orders. Okay, then the sort method is called stable. Otherwise is here 7 2 comes first, then 7 1. It's quite different orders as input data. Then this sorting method is called unstable sorting. Okay, the stable sorting algorithm is here: insertion sort, merge sort, bubble sort, counting sort are belong to stable order, stable sorting algorithms, and the unstable is called selection sort, heap sort, shell sort, quick sort. Okay, among these sorting algorithms, insertion sort, merge sort, and heap sort, and selection sort will be studied in our class. Okay, so we can distinguish which algorithm is stable sorting algorithm or which algorithm is unstable sorting algorithms. Now we can go on to the insertion sort method, the first sorting method. Okay, insert a record Ri into a sequence of ordered record. Yes, these are already ordered record, and I want to insert new record Ri into this ordered method, ordered record. That is the inserting sort method. This algorithm time complex is a big O n square, and this belongs to the stable sorting method, and this is very fast when n is very small, data is very small. This insertion sort is very fast. Okay, this is an example of insertion sort. Okay, we are given this is input. Unsorted data are given, then we will start from the first element here, 26, and go on to the next one is here. Okay, 5. We will compare 26 and 5. 5 comes first. So this 5 comes first and the 26 is next. Now go on to the next one. Okay. Next one is 77. Okay, it satisfies the ordering here. So we will go on to the next one. 1. Value is 1. Okay. Then 1 should we go first because it's the smallest value, and 5 goes to the next. 26, 77 it goes to the next. Okay, next go on to the next value, 61. Okay, 61. We must insert 61 into the already sorted data. Okay, we can find the right position in here. So 61 is inserted here, and 77 will go to the next element. In this way, we will sort data one by one. Here, 71 is inserted at these positions after 5, between 5 and 26, and the remaining data will be moved to the next element, next positions. And the next one is 59. So 59 position is here, and the 15 position is between 11 and 26, and 48 will go to this position. 19 goes to the these positions. Okay, so this is a last element in the input data. So this is a result output of the sort of this insertion sorting method. Okay, so this is an insertion sort method. So you can understand how you can sort using this insertion sort method if you are given some data set. Okay, yes, I think that's enough for our class. Okay, we will go on to the second sort method is a quick sort. Quick sort. Okay, quick sort is called CAR whole method. Okay, it's I think this method is invented by these persons. Okay, so the given data set is R0, R1, Rn minus 1. N records are given. Then we can pick up pivot key values Ki. Then Ki is placed in position Si. Then all of the data is Kj index value is smaller than Si. Then all of the data is smaller than Ksi. And index greater than Si, key values are greater than Ksi. Okay, so that means that this RSI is a pivot key record. Then the left part is smaller than this RJ, smaller than this R key values, and the right part is greater than the key values of RSJs. So we can divide two parts of the given data set. Okay, so we can, yes, this is a detailed implementation of a quick sort. Okay, this quick sort input parameter is a data set, and the left and the right index are given as an input of this quicksort algorithms. And we compare left and the right. Left is smaller than right, and the I value is set as a left, and the J value is right plus 1. Yes, plus 1 is added because it will decrease first here. So in order to start from right, exact value of right, we have to increase 1. Okay, here. And left is not added by 1 here. So we will compare as the second value, second to the left value is used in this do loop statement here. Pivot value becomes least left value. Yes, the left value becomes the pivot value. That means that we will use left and right value here. Okay, so there are many data can exist here between this left and right. So this left value becomes pivot value. The first data becomes pivot value here, and then we will start from the second to the left here, because I plus 1 means that we will increase 1 to the left. So that means that we will start from the second element to the left here. Then we will compare this second value with pivot value. And we will continue this loop while this key value is smaller than pivot. And it will stop when key values are greater than or equal than pivot. Can you understand that? Yes. If the key values are greater than pivot, we will stop there. So the I values are determined when key values are greater than pivot. And J minus minus means that we will decrease J values by 1 until key values are greater than pivot. Okay, that means that if we meet key values are smaller than pivot, then we will stop there. Okay, so J values are determined when key values are smaller than pivot. Okay, so we will search this direction at this first line, and do J minus minus means that we will start from right to the left. Okay, so the found I and J will be compared. If I is smaller than J, then swap these two values. Swap means that exchange the location, list I and list J. Okay, this will be continuous while I is less than J. Okay, that means that we will stop when I is greater than J. Okay, and that means that this first line goes to the right, and the second line goes to the left. If they are meet, okay, I will draw this one in here. If they meet some point here, then I values becomes greater than J. That means that it goes to the right, and this goes to the left. Then it will stop. After stop, swap list left and list J. Yes, the found J is used here and exchange the pivot value and list J values here. Okay, so these are quick sort algorithms, and the left part will be applied quick sort again here, and the right part also will be applied using this quick sort self recursive functions here. Okay, this is a quick sort algorithms. Okay, it looks very complex, but if you look at example, then you can understand well. Okay, now let's go. Okay, this is a quick sort example here. So if we are given this 10 record, 10 datas here, 26, 5, 37, 1, 61, 11, 59, 15, 48, 19. Okay, so this is first line. Okay, so in here, left value is 1, right value is 10. Okay, at the in the algorithm we have seen in the previous slide, this 26 is selected. The first record key values is selected as pivot value, pivot. And we will continue to search from left to the right using I index, I++ do loop index, and also we will continue to sort to compare data with 26 pivot values. Okay, 5 is less than 26 pivot value, it's okay, and goes to the next one here, and 37 is greater than 26. Okay, so here we have to stop. So the I value becomes 3 here, and then next do loop, J do loop start from right +1, and it will decrease. That means that it will go to the left from right. Okay, so 19 will be compared with 26. If 19 is less than 26, yes, already J values are found here. So J and I, J values and I value, J value becomes 10. Okay, so we will swap this 37 and 19. So 19 goes to here, and 37 goes to here. Okay, swap. So swap means that exchange here and here. Okay, and then continue. Continue to go on to the I go to the right 1. Yes, it's less than 26, and but this one 61 also found. I is 5, and 48. Next we will continue to search J values, next J values. So J value 48 satisfies. Okay, go to the one more, but this is less than 26. Okay, so another J, next J is found as 8. So 61 and 15 values are swapped. So 15 goes here and 61 goes here. Okay, next go to this one here, I here, and the J, and it is okay, and 59 is not okay. So I becomes 7, and then J continues to go to left. Okay, so this is okay, and this one, okay, 11 is less than 26. Yes, J is found as 6. So it will check that I is less than J value. Okay, it is violated. So we will exit the loop statement, main loop statement. At that time, J is 6 values. After exit the main loop, we will swap again with pivot value and J values. Okay, so this 11 is 11 goes to left value, and the 26 pivot value comes here, 26. Okay, so the result of the first step, first phase of a quick sort becomes this one. Okay, 26 was pivot value of the previous phase, and then the location of 26 is determined as J value. J value index was 6, so here 26 location is here. And then we have left part and right part. Okay, so we will visit left part first. So in here, left value is 1 and the right value is 5. The same way, we will apply quicksort on the left part here. Okay, so we will select 11 as pivot value, and we will continue I value here, and from the second to the left. Okay, so 5 is less than 11, so it satisfies and goes here. Then 11 is greater than, 19 is greater than 11, so I value becomes 3 here. And then we will start from right value here. So 15 will compared with 11. Yes, it is satisfied, greater than 15, so go to the next one. So 1 is less than 11, so J found the J values is 4. So this 19 and 1 will be exchanged. So the temporary value of this 1 is here and 19 is here. and going on to increase I values, okay, and the I values are here 15, so I is 5, and decrease J values here, uh, okay, J is 3, so it violate I should be less than J value, so it will exit, and then exit the main loop. We will swap pivot value and the J value. J is 3 here, so 1 is there at that time, and 1 and pivot value 11 will be swapped. So 1 goes here and 11 goes here. Okay, yes. It may looks very complex, but if you understand, it is a very interesting to you. Okay, and now also we will go on to the left part of the this step. Okay, so but already 1 and 5 satisfied here, and 11 here, and this one components are 2 here, so we will exchange here 15 and 19. Of course, you can apply the exact quick sort algorithm in 2 data set here, but simply we can see that we will switch 15 and 19. Okay, now we can go on to the, okay, this one is the result, and now we can go on to the right part of this one. So in this case, left value is 7 and the right value is 10. Okay, so 59 is selected as pivot, and I goes from second to the left here. So 61, okay, already found. I becomes 8. And J goes from here, 37. Okay, 37 is less than 59, so J is also found, 10. So we will exchange or swap 61 and 37. 37 goes here, and the 61 goes here. And continue to go to right. I value and 48 is less than 59. Yes, it's satisfied. And goes here. 37 is also satisfied. So now I is 10. And how about the J? J goes here and here. So J is 8. Okay, now I should be less than J. It violate that one. So no. J was found here. Okay, so J is 9 because 48 is less than 59, so J is found here, 9. Okay, so we will exit. So I is 10 and J is 9, so it violates the main loop. So we will exit the main loop here, and J value is 9, so we will swap pivot value and J value. So 48 goes here and 59 goes here. Okay, so left part of this line is 48 and 37. There are two elements here, so we will exchange. 37 goes here, 48 goes here, and 59, 61 is here. Okay, 61 is only one element in the set, so 61 is here. Okay, so that's the final result of this quicksort problems. Okay, if you understand well, you must examine all of the data here in detail, and then you must understand how it works well. Okay, that's very interesting to you also. Okay. Okay, the quicksort algorithm time complexity analysis result is here. Okay, so if you see this time complexity in here, then our time complexity analysis average case is most important. Okay, so you must remember average time complexity of quicksort, that is big O n log n. Okay, so as we have seen, this n log n time complexity is optimal sorting algorithms. Okay, so but unfortunately, this is unstable. This quicksort is unstable algorithms. Okay. Okay, the variation can exist over this quicksort. Our current version uses that pivot value. Okay, so we picked the key of the first record as the pivot values. Okay, so we will improve these versions by changing the choice of the pivot as the median of first, middle, and the last keys. Okay, there are three values: first, middle, and the last keys. Okay, among them, we will select median values as a pivot. So it will increase the speed of the quicksort, I think. So that's the variation of quicksort. And okay, so the optimal sorting time complexity is a big O n log 2n is well known as the best or optimal sorting algorithms. Okay, and the last sorting method is merge sort. Merge sort. Okay, so two sorted list can be merged into single sorted list. Okay, so this is iterative merge sort method, is the general merge sort method, and we can start from the n sorted list with a length 1, so only single element sorted list is the start point, and then we can continue to the to merge the pairwise size 2 uh, size 2 subset into a single merged set. So we can continue to a single list remains. Okay, so that is a merge sorting method. So this is an example of the iterative merge sorting example. This is given, these are given data set here. So we will start from the size 1 single merged data set here, and then we will merge this single data to make size 2 merged data set. Okay, so if we merge 26 and 5, 5 goes first and the 26 goes next. And the 77 and the 1 will be merged as 1 and the 77, 11 and 61, 15 and 59, 19 and 48. Okay, that is a first result to make a size 2 merged output, and then we will merge again to make size 4. Okay, so 526 data is merged with 1 and 70. So 1 is goes first, and the 526 and the 77. And the next one is 11, 15, and 59, and the 61 is the last one, and the 19 and 48 remains the same because there are nothing to merge here. And the next one is merge 4 size 4 data into size 8 here, and 1, 5, 11, 15, 26, 59, 61, 77 is the result of a merged data set. And last one is merging these two subset. Okay, the last one is here. So here, if we analyze time complexity, then how many paths? This is one path. Path 1, path 2, path 3, and path 4. So how many passes are necessary in here? So log to n passes are necessary here, and in this each pass we need big O times. Big O n times are necessary here. So the total time complexity is here. Big O n log n. Okay, so that means that this iterative merge sort algorithm is best sort algorithms until now. So this is very efficient merge sort method. We can skip. And the last one, heap sort, is here. So we already have learned what is heap in here. So heap, max heap and minimum heap exist existing type. So we will consider only max heap. So we will use max heap to sort some data set. Okay, so this one is heap sort examples. So this is not currently, this is not heap, but instead it is binary search, binary trees now. But we can convert. Yes, this is a heap sort examples. Okay, so you can see that this is a heap because every parent node values are greater than children's values. Okay, 77 is maximum value, and 61 is the maximum value of its children's. Okay, so this is a heap. Now, how can we sort these data? Okay, so we already know that the 77 is maximum value, so this root node will be exchanged with the last node. Okay, so 5 goes here and the 77 goes here. Now we must heapify all of the data except this data. Okay, so 5 will be exchanged with great value between these children. 61 goes here and 5 goes here. And the 5 will also exchanged with 48. 48 is here and 5 goes here. Now 5 goes to here. So 5 is here and 15 goes here. So this is a result of a heapify. Okay. Second one, okay, that is explained here. Next one. Okay. Next one, this 61, the maximum value will be exchanged with the last one. Okay, so 1 goes to the root and the 61 goes to this last one. And then we will heapify this binary trees. So 1 goes to here. Okay, 59 is greater than 48. So 1 goes to here. So 59 comes here and 1 goes here. And the 1 and the 11, 26. 26 will be exchanged with here. 26 and the 1 is here. Okay, that is the next result of the heap sort. In this way, we can continue to the end. Okay, so now 59 will be exchanged with 5 and then heapify. That result is here. And next one is a 48 and the last one is a 1. So that is exchanged and heapified. And the next step is here. So 26 is current root node, and we can exchange this 26 and the last element because this part is already searched, already ordered. Okay, so the last element is here 1, so we will exchange 1 and 26 here and include this as here and heapify this 1 in here. So 1 goes here and 19 is here, and 1 goes here and 15 is here. Okay, so that's the result of this current step. And we will continue to root node here. So that's the result of a heap sort. Okay, that's all. That's all of chapter 7 here. So we studied the several sorting algorithms. So you must understand every sorting algorithm in this chapter. And in some case, you must understand the detailed algorithm itself, and also you must understand the example. If you are given some data set, you can apply in any sorting algorithms. So I will make some question about this sorting algorithms in final exam also. Thank you for your attending this class, and that's the last class in this semester. Thank you again. See you.